today we have really one big goal, and that's to nail down a formal definition of independent events and learn how to show the calculations to back up whether or not two events are independent. So we're going to actually go back to where we first met disjoint and independent in chapter 13 and just refresh some big ideas and add to. So we defined disjoint events in the last chapter as two events that have no common outcomes. We looked at a Venn diagram with two circles that don't overlap, so nothing in common. There was another name. These were otherwise known as mutually exclusive events. Those are interchangeable terms. And one of the hardest things I think to nail down is that disjoint and independent are two very different things. They have links to each other, but they are not the same idea. So not the same as independent events. And I remember even after that first year of teaching AP Stats, I had students calling me from college saying, tell me one more time, what's the difference between independent and mutually exclusive? Because they were still struggling with that. So independent or mutually exclusive or disjoint is the easy one. Do they share common outcomes? Yes or no? If they do, they are not disjoint. If they don't share common outcomes, they are disjoint. So that's a real simple check to see what the outcomes are. So there's no calculations to do. It's not complicated. Independent is more complicated because informally, independent means that the outcome of one event or trial doesn't affect the outcomes of the other. So the probability that event A happens doesn't, or the fact that event A happens doesn't affect the probability of event B happening, which involves some probabilities, which involves usually some computation. And to kind of help with that, let's take a real quick trip into the textbook. There's just a short snippet on page 370 and 371. And I don't trust that all of you will go read it on your own because that's just not what you do. So we're going to, since I'm not here, I'm still going to make you read it. So here's our picture of disjoint events. A and B do not overlap. They do not have any common outcomes. And this is a little snippet in the textbook about the fact that independent is not equal to disjoint. And being the experts, the authors of the textbooks, they say it better than I do. So we're going to take a look at what they say. Are disjoint events independent? These concepts seem to have similar ideas of separation and distinctness about them, but in fact disjoint events cannot be independent. All right, let's jot that down first. First of all, disjoint events cannot be independent. So if two events are disjoint, they automatically are not independent. And let's make a note here. See page 370 to 371. Now, we're going to finish reading this snippet to give an example or something to maybe help it make sense why that's true. So we're going to go back to here. Let's see why. Consider the two disjoint events. Event A is you get an A in the course, and event B is you get a B in the course. They're disjoint because they have no outcomes in common. Suppose you learn that you did get an A in the course. Now what is the probability that you got a B? You can't get both grades, so it must be 0. So getting an A changes the probability of B to 0. Think about what that means. Knowing that the first event, getting an A, occurred, changed your probability for the second event down to 0. So these events are not independent. Now there is a little footnote down here, usually a little tongue-in-cheek comment. Technically, two disjoint events could be independent, but only if the probability of one of the events is 0. In other words, one of the events can't even happen. For practical purposes, we ignore this case. After all, statisticians don't anticipate having data about things that can never happen. So we don't even worry about that issue. Back to where we left off here, disjoint events can't be independent. They have no outcomes in common, so if one occurs, the other one can't. A common error is to treat disjoint or mutually exclusive events as if they were independent and apply the multiplication rule for independent events. And we don't want to make that mistake. Now, the multiplication rule that we learned back in chapter 13 hinges on independent events. So we've got to be careful about knowing whether the events are independent before we apply it. So we're going to summarize. Two events could be either independent or disjoint, but they can't be both. If you're disjoint, you can't be independent. We've already jotted that down. Okay, the second that we haven't jotted down is they could be neither. You could have two events that are neither disjoint nor independent. Let's jot that down, and then we'll read one more little section about why. So events can be neither disjoint nor independent. So you can be one and not the other, or you can be neither. You can't be both. To try to drive that one home, they give another example at the top of the next page. One spring day, your high school baseball team will be playing for the league championship right after school. You and your friends are planning to go, but when you look out at lunchtime, it's raining. Consider the events are rain at lunchtime and B, baseball after school. They're not disjoint. Even though it's raining now, the game may still go on as scheduled. And they're not independent either. You thought you were going to the game, but now that you see the rain, you're not so sure anymore. Knowing rain at lunchtime, R, changes the probability of B going to the baseball game. Now, moving on to the big stuff. Disjoint, not hard to determine if two events don't share common outcomes. However, independence is a little trickier. So we've kind of skirted around independence. We've looked at graphs of segmented bar charts back in earlier chapters and tried to decide if two events are independent based on the bar charts. We have yet to get a formal definition of independence. And that's really where we've got to go next. And that's why we learned what conditional probability was yesterday, is because independence hinges on the definition of conditional probability. So let's go on to the next slide and dig into the big stuff. Formal definition of independence. If you are asked on the AP exam to decide if two events are independent and they give you some probabilities, you're going to actually have to do some calculations to back up a yes or no answer. So the formal definition, which is not in your blue book, you have to just know it, is here. Two events A and B are independent if the probability of B given A, this is a conditional probability, is equal to the probability of B. Which means you've got to compute two probabilities. If they're equal, you have independent events. If they're not equal, you will not have independent events. So it all hinges on whether two probabilities are equal. Okay, notice something that these two sides of the equation have in common. They both calculate the probability of B. The difference is, on this side, we have a given A. If A occurring changes the probability of B, then this side would be not equal to this side. So if A changes B, then we would not have independent events, and this would not be equal to this. So if the given doesn't change B's chance of happening, in other words, if A doesn't change B's chance of happening, if A occurring does not change the probability of B, then the probability should be the same as if A wasn't considered. And the two sides would be equal. So if given A gives you the same probability of not given A, then A didn't change B, and the two events are independent. How do we apply it? So that's what we're going to dig into for the rest of today's lesson, and that will be the quicker part, because it's just about computations. Alright, moving on. Alright, so here's an example. Probability that a U.S. resident has traveled to Canada is 18%, Mexico is 9%, and to both countries is 4%. So both countries means they've traveled to both Canada and Mexico. This 18% is just to Canada, this 9% is just to Mexico. We want to know the probability that someone who has traveled to Mexico has visited Canada too. Alright, someone who has traveled to Mexico, that's a condition. That's a given. So this is a conditional probability. In symbols, we're going to write this as probability that someone who's traveled to Mexico, so given Mexico, has visited Canada. So the probability of going to Canada, given that we've traveled to Mexico. Conditional probability, what we learned yesterday. Alright. So we have a formula for this, and we need the formula because these are not counts, these are percentages. If you had counts, you wouldn't need the formula. The formula says that this probability is the probability of the intersection of Canada and Mexico. In other words, this is the probability of going to both countries, Canada and Mexico, over the probability of the given, which is going to Mexico. Alright, we know both of these numbers. The probability of going to both countries is 0.04. That's your top number. The probability of going to Mexico in general, anybody that went to Mexico, is 9%. And I misspoke a couple of minutes ago when I said this Canada 18% is people who only went to Canada. This 18% actually includes the people that traveled to both. And the 9% Mexico includes the people who went to both. When you divide this, we get 0.4444444. It's a repeating decimal, so about 44.4 is your probability and percentage of going to Canada if you have been to Mexico. Okay. Our travel to Mexico and Canada disjoint events explain. Okay, disjoint events means there are no common outcomes. So is it possible for people who've been to Canada also to have been to Mexico? Do Canada and Mexico in a Venn diagram overlap? Well, they do, because we have 4% of the people who've been to both. So disjoint, no. And the reason is some people travel to both Canada and Mexico. Disjoint's the easy part. Do we have overlapping in our Venn diagram? Yes, we have people who've been to both. Both events could happen to the same people. So disjoint's the one we like because we can explain that one in one short sentence every single time. Independence, that's a little more complicated because independence, now that we have a formal definition, requires a computation. Are travel to Mexico and Canada independent events? Explain. Well, the explanation is primarily number crunching. So, if the probability of Canada given Mexico is equal to the probability of Canada, that's the formal definition that we would have independent events. Now, stop right there and note that order doesn't really matter. We could do probability of Mexico given Canada equals probability of Mexico and accomplish the same goal, as long as the first event on the left side matches the event on the right side, then you have it set up correctly. The reason I chose this order is because I've already calculated Canada given Mexico. Why should I redo it? Let me just use what I already have. Okay, so let's fill in some blanks. The question is, are these equal? So really there's a question mark there. Probability of Canada given Mexico we've already computed. That was 0.444. Is that equal to the probability of going to Canada? This is anybody who's gone to Canada, which is the entire 18% of Canada that we had back here. So 0.18 is the probability of going to Canada. Is 0.444 equal to 0.18? No, it's not. So those are not equal. So we're going to say probabilities are not equal. So the two events are not independent. Not equal, not independent. Equal means independent. It's a really easy computation. You just have to know how to set it up and show both sides equal or not equal. Learn the definition. Okay, let's do one with a deck of cards. Alright, by now hopefully you know what's in a standard deck. If not, you have that in your notes. You should go back and study it. Are drawing a red card and drawing a spade mutually exclusive events? And explain. Okay, are any red cards spades? Do we have any cards in the deck that are both red and a spade? No, they're not. So red and spade have no overlap, no shared outcomes. So we're going to say that these are disjoint because they don't share outcomes. So are the events mutually exclusive? Yes. And explain. There are no red spades in the deck. When you give your explanation, make sure that it's in context. Don't just say there are no common outcomes. You have to be in context. Talk about cards, talk about colors, talk about suits. Second question, are drawing a red card and drawing a spade independent? Totally different question. Calculation is required for this one. So we could start with red given spade or spade given red. Doesn't really matter which way you do it. You just pick one and go with it. So we're going to start with probability of, let's do red given a spade. And we want to know whether or not that's equal to probability of just having a red card. Does given a spade make a difference? That's the question. Okay. Red given spades, if I can count cards I can count, I don't actually need the formal definition of conditional probability. I can just count cards. Given spades means spades has to be the bottom number. How many spades do we have in a deck? Well, spades is a suit, and each suit has 13 cards. So it's 13 cards that are spades in a deck of cards. Of those spades, how many of them are red? How many are red spades? And that's a 0. None of those are red spades. Is that equal to the probability of a red card? Okay, red cards. How many cards are red? 26. Out of how many total cards? 52. Or if you already know that that's 1/2, half the deck is red, you could go ahead and use 1/2 there. Either way, 0 is not equal to a half. Those are not equal. So the events are not independent. Well, I can't spell. Since the probabilities are unequal. The work is the calculations, but you have to follow it up with some sort of a summary statement. Write the sentence. You have to say the answer and why. Make sure that's all there. Short and sweet, one sentence will do it every single time. Alright, there's one more slide and we'll be done with today's notes. So let's move on. Back to the standard deck of cards. We're going to draw one card from a standard deck. So if we pick one card, are red card and ace mutually exclusive events? Well, are there any red cards that are aces, or any aces that are red cards? Yes, we have an ace of hearts and we have an ace of diamonds. So are they mutually exclusive? Nope. Two cards in the deck are red aces. Okay. Short and sweet, mutually exclusive, that's the easy one. One sentence will do it. Don't forget the yes or no. Are red card and ace independent events? And explain. Okay, red card and ace. I could do red given ace or ace given red. It doesn't matter. Just pick one. I'm just going to do them in the order that they're in the problem here. Probability of red given ace, is that equal to the probability of red? Okay. How many aces are in the deck? We can count cards. Aces are a total of 4. How many of those aces are red? In other words, how many red aces do we have? That's 2. Is that equal to the probability of red? Well, there are 52 cards in the deck, 26 of which are red. 2 over 4 reduces to 1/2. 26 over 52 reduces to 1/2. 1/2 is equal to 1/2. Those are independent events because we have equal probabilities. So let's write a quick statement about that. Probabilities are equal, so the events are independent. Okay, that's it for today. You have day 3 homework already written in your notes, so you can spend the rest of the period working on that. I suggest you check your work as you go along, and we will pick it back up again tomorrow.